Hey dudes, we'll try not to switch it up too much this time. This is 5.3 simple circuits, and looking at V equals IR, we did a little bit with that. It's going to come back into play here. Let's try another topic 1 question. Try that out, pause me. Okay, so we're talking about the side length of a cube. So here's our cube. It's a certain length. It's 2 centimeters plus or minus 4%. We might be off. And the mass is this, right? So now we're trying to calculate density, and we want to find the uncertainty. Well, density is mass divided by volume. And I know the mass, grams per milliliter. The mass is 24 plus or minus 0.8. So this is 8% uncertain already. And then we're going to divide by the volume, but the volume is length times width times height, which are all the same. And so essentially it's 2 plus or minus 4%. 2 plus or minus 4%. 3 times. So really the uncertainty is this is 8%. And 3 sets of this, because it's saying length times width times height, so that cubed. So it's 4 sets of these. Sorry, 3 sets of 4%, which is 12, 8, 20. I think that. Yeah. Cool. Be careful with those. Okay. If you were here, if I was here, I would. This is a good demo. I like the idea of water in current flow. So if we had a tank of water, we'd pump some water up to the tank. It's not the pump that's doing the pressurizing. It's the difference in height from here to here as our water returns down, right? And as the water flows back down here, right, it sprays out of this hose. It'll spin this paddle wheel, and if you have higher flow, you get a higher speed or higher spin of the paddle wheel, right? So one thing that might make this spin faster is higher velocity water. So if we pick the tank up higher, you'll have higher potential energy here, right? Which means that the water coming out, same size tube, but will come out with a higher kinetic energy, and therefore should spin your wet wheel faster, right? So this is our potential energy changed here, our height, our gravitational potential energy. Therefore, our kinetic energy changed, so this will give us a higher flow than this one. This has the same potential, this part C has the same potential energy here. But what's happening is we're letting the water out of the tank in a bigger chute, right? So the water's coming out, and it doesn't have to go through this little tiny nozzle. It all comes out in one big gulp. You could think about it as this. If you had a bucket and you cut a little hole in it, water would come out. And if you, let's see, let me grab all this, slide it over, and if you took that bucket and poured it on the water wheel, you'd spin the water wheel, right? And if you pick the bucket up, higher velocity, the water wheel would spin faster. Well, another way you could make the water spin faster is not use the hole, it's just flip the bucket over, and then you get, instead of a little bit of water coming out, you get all of the water coming out, and that'll spin the bucket or the wheel faster, even though you haven't raised it at all. Now, of course, both are better. If you can hold it way up high and dump it, that's better. But one way to increase the amount of oomph that comes out of it is increase the height. Another way is to flip it over. Yeah. And dump more liquid per time. So those are the two ways that we can change the amount of spin, right? The flow, if you will. All right. Da, da, da. So one of the ways to move charges is with an electric cell. We might call it a battery, and all it is something to create a potential difference, right? A difference in charge. One of the most basic ways to do this is with different metals that have different electrical properties. So really, basically, you could use copper and zinc, and you put them in an acid bath. And when you put them in an acid bath, the acid dissolves the copper and the zinc, but because one is softer than the other, it dissolves the zinc a little faster, which leaves it with more negative charge because it doesn't pull all the electrons off with it as it dissolves. So it leaves some electrons behind as it dissolves. You'll see it bubble. I'll show you in a second. The copper doesn't dissolve as fast, and therefore it doesn't have as many negative charges left. So you're left with two plates with unequal charge. Right? This has an excess of negative charge. So does this. They both have excess negative charges, but the copper has more excess negative charge. And so if we could connect them like that with a cable, these negative charges would be repelled by each other and pushed over to a lower concentration. And that's the potential difference that we're making. And you can see this, like, it's just copper and zinc and acid, which is just like water. If you, let's see. Yeah. So it's copper and a zinc plate. That's acid, and you can tell it's acid because you can see it bubbling. And there's nothing in here. There's no batteries. It's just metal and acid. I hope I'm still on your screen someplace. And you can see this bulb light up as this dissolving occurs. Yeah? And so the bulb's lighting up. There's nothing in there except acid dissolving, leaving an imbalance of charge. And the imbalance of charge is walking it through the light bulb, and we're harnessing it to do something useful, like give light. So that's a simple battery, a cell. And on a schematic, it looks like this, with a long side and a short side. Essentially, it's a high potential and low potential. So this is the copper side and the zinc side. I guess they are switched here. They'd be like that. But it's just long side, short side. That's a DC circuit. All right. Sometimes in batteries there's some resistance interior, which is just natural. You're going to have some resistance within the battery. So sometimes they'll put in a battery symbol, a cell symbol, with a little resistor right next to it, and this is the resistance of the cell. Most of the time we'll consider it 0, but it's not always 0. And then this electromotive force, we use this little scripty E, is the work done moving charges from the potentials from low to high. And the unit of electromotive force is 1 volt. So the most basic thing you can do with an electric circuit is close it in a loop. You have a source of electrical potential energy. You have a load. If you don't have a load, you get a short circuit. We'll talk about that more later. But you want to do something with these moving charges. So we have a little resistor, and you have the electrons moving from a high to low concentration. This is the conventional current, meaning the positives want to move this way. Really, it's the electrons that are moving this way. But we say the conventional current is that way. The electrons are going from high density of negatives to high density of positives, so they're walking this way. You could think about that again in the sense of liquids being moved from higher and lower gravitational potential. So the battery sort of pumps water molecules up to a higher level. The water molecules have some potential energy because of their height, and as they come down, they go through they walk through some resistance, and they burn off their gravitational potential energy, and that PE goes into KE or something else, maybe thermal, etc. Oh, it's hiding back there. But a couple of things is if you made the resistance heavier, like if you made two of these resistors in here, right, or you made this resistance bigger, you would get less current flow. So if the resistance increases, the current's going to decrease. Also, if you make this change instead of this much potential, I guess they did it in red, instead of this much potential, if you made the potential higher, went from here to here, and so this is flowing downhill like that, and then across, and these charges were going all the way down and losing this much potential energy, you'd be increasing the V, and therefore you'd be increasing the flow. You'd get much more flow of these electrons through there. I know they're positives moving right now, but so this is the same water analogy that we were working with before. With an increase in resistance, will increase the will decrease the current, and an increase in pressure voltage will increase the current. We kind of walked through that already. Okay, so even if you don't have a as simple circuit, like if we include the resistance of the battery, we can still calculate the overall resistance. There will be a drop, there will be a little resistance here, and a resistance here. If this is you have some voltage, some pressure pushing electrons through this R and through this R. You could think about it as water is being pumped up, has to go down, flow down this little staircase, which loses some energy, and down this staircase, which this loses some energy. So this one is this one is that. But the same thing happens. The voltage, the pressure, is related to the current and the resistance. We just have two of them. We have a resistor up here, and we have a resistor here. So, sorry, it's got kind of messy. So this electromotive force, I'm going to call it V again, is the voltage drop from the small one plus the voltage drop from the big one. We'll do this again with more basic calculations, but you can find the flow through the components individually. So let's try that out with a problem. We have a 9-volt battery. It has its own internal resistance, which we're going to treat as a separate resistor. It's connected to a 2-ohm resistor, maybe a light bulb or a little motor. How much current will flow? All right. Well, I know that the pressure makes the current flow through the resistor. So we could talk about there's two resistors. There's this 1-ohm resistor, there's a 2-ohm resistor. In total, there's 3 ohms of resistance. So I'm going to call this V. I know there's subtle differences, but so this is 9 volts. If we divide this out, you could say I is V over R. We have two resistors, a 1 ohm and a 2 ohm, so that's in the denominator, and so you get 3 amps of current coming through here. And they are asking what's the potential difference across the 2 ohm resistor. They're just wondering how much potential energy does it lose from here to here as it goes down this staircase. So it goes down this staircase first, it loses this much potential energy. This one loses that much potential energy. So they're looking at this potential difference, right, the change. So we know that the V equals IR, the potential difference is really the current times the resistor. We know the current through the whole system is 3 amps, and the resistor is, oh, I think this should be 2 ohms. That doesn't make sense as a V. I think this is ohms. Through 2 ohms, and so the 3 times 2 gives you the 6. The V is in volts. Cool. Try out 15 and 16. Those are your 2 problems, and then go back and see if there's anything else you missed.